Right. Hello, everyone. My name is Sam, and I am from the Blockhead. It's an educational resource that talks about cryptocurrency and blockchain in an easy, entertaining way. Today, we're going to cover Intro to Blockchain for the next hour. I'll briefly cover what is on the agenda. We'll go through some different principles, some technical, some more high level, and then we'll finish up with some group work. So today we're going to first cover what is blockchain. We're going to really look at the basics, how it came to be. Second, we'll go into more how it works. So actually, how does blockchain technology function? Then we'll get into some technical details. I pulled these out because these are probably the hallmarks of blockchain and really what set it apart from other types of ledger technology. And then fourth, we'll kind of zoom out into the bigger picture and look at the use cases today. Now, I will be showing a couple of videos throughout the workshop. There also is one or two slides that you've seen before if you've been in the previous workshops of centralization versus decentralization, as well as intro to crypto. If you haven't watched those yet, I highly recommend it. They're a great precursor and really lay the foundation for what we're going to be covering today. All right, so what is blockchain? We've heard this word a lot in recent years, and it's continued to pick up steam. It's kind of becoming a buzzword, but what are we actually talking about here? So blockchain is a type of technology, and it was introduced in 2008 as part of the Bitcoin white paper. If you're not familiar, Bitcoin is a cryptocurrency, and a white paper is essentially a paper that describes a problem and a solution. So Bitcoin came out as a peer-to-peer network. We'll look at a brief clip of that white paper and how it talks about the peer-to-peer network system. But blockchain was a fundamental part of that introduction. It basically allowed cryptocurrency to be built. Now, blockchain is a distributed ledger technology. A ledger is essentially a spreadsheet, and it's a way of keeping record of something. Now, although this seems really dry and a little obtuse, basically, we use ledgers in our everyday lives. They keep track of everything. They're behind our Google Calendar invites. They're tracking what's going in and out of something, whether it's a transaction or it's basically the record keeping that is the basis for a lot of our systems today. It can even be, energy that we use or transportation. There are limitless use cases for how we record different information. Again, blockchain is the basis of Bitcoin and other cryptocurrency. It was a way to establish digital trust, and it really gets its properties from cryptography. So when we talk about cryptography, we're really talking about encryption, which allows data to remain private and secure between two confidential parties. When we talk about these types of things, it's important to remember that, maybe 40 years ago, if you wanted to get a piece of sensitive information to someone else, you would probably have that on a sheet of paper. That sheet of paper would then be put into a folder that conceals the information. And then you would hand that folder to your friend, who would then open the folder in order to read the document that's confidential. But on the internet, how do we do that? How do we do this in a digital space? So that's what cryptography does. It's essentially that folder that we put on top of the data that we're trying to transmit so that it remains secure. And we're going to go into encryption later in more detail because there are many different types, but know that that's a key piece of why blockchain is so valuable. And again, this just basically establishes digital trust, something that we haven't really had in the internet since it began. Now, what is blockchain? So we have 3 videos. This is the first one today. They're all between 5 and 10 minutes, so they're quite short, but I think they do an excellent job of describing really the fundamentals of blockchain in a very visual, compelling way.
Many people think of blockchain as the technology that powers Bitcoin. While this was its original purpose, blockchain is capable of so much more. Despite the sound of the word, there's not just one blockchain. Blockchain is shorthand for a whole suite of distributed ledger technologies that can be programmed to record and track anything of value, from financial transactions to medical records or even land titles. You might be thinking, we already have processes in place to track data. What's so special about blockchain? Let's break down the reasons why blockchain technology stands to revolutionize the way we interact with each other. Reason number one, the way it tracks and stores data. Blockchain stores information in batches called blocks that are linked together in a chronological fashion to form a continuous line, metaphorically, a chain of blocks. If you make a change to the information recorded in a particular block, you don't rewrite it. Instead, the change is stored in a new block, showing that X changed to Y at a particular date and time. Sound familiar? That's because blockchain is based on the centuries-old method of the general financial ledger. It's a non-destructive way to track data changes over time. Here's one example. Let's say there was a dispute between Anne and her brother Steve over who owns a piece of land that's been in the family for years. Because blockchain technology uses the ledger method, there is an entry in the ledger showing that Adam first owned the property in 1900. When Adam sold the property to Dave in 1930, a new entry was made in the ledger, and so on. Every change of ownership of this property is represented by a new entry in the ledger, right up until Anne bought it from their father in 2007. Anne is the current owner, and we can see that history in the ledger. Now, here's where things get really interesting. Unlike the age-old ledger method, originally a book, then a database file stored on a single system, blockchain was designed to be decentralized and distributed across a large network of computers. This decentralizing of information reduces the ability for data tampering and brings us to the second factor that makes blockchain unique. It creates trust in the data. Before a block can be added to the chain, a few things have to happen. First, a cryptographic puzzle must be solved, thus creating the block. The computer that solves the puzzle shares the solution to all of the other computers on the network. This is called proof of work. The network will then verify this proof of work, and if correct, the block will be added to the chain. The combination of these complex math puzzles and verification by many computers ensures that we can trust each and every block on the chain. Because the network does the trust building for us, we now have the opportunity to interact directly with our data in real time. And that brings us to the third reason blockchain technology is such a game changer. No more intermediaries. Currently, when doing business with one another, we don't show the other person our financial or business records. Instead, we rely on trusted intermediaries, such as a bank or lawyer, to view our records and keep that information confidential. These intermediaries build trust between the parties and are able to verify, for example, that, yes, Anne is the rightful owner of this land. This approach limits exposure and risk, but also adds another step to the exchange, which means more time and money spent. If Anne's land title information was stored in a blockchain, she could cut out the middleman, her lawyer, who would ordinarily confirm her information with Steve. As we now know, all blocks added to the chain have been verified to be true and can't be tampered with, so Anne can simply show Steve her land title information secured on the blockchain. Anne would save considerable time and money by cutting out the middleman. This type of trusted peer-to-peer interaction with our data can revolutionize the way we access, verify, and transact with one another. And because blockchain is a type of technology and not a single network, it can be implemented in many different ways. Some blockchains can be completely public and open to everyone to view and access. Others can be closed to a select group of authorized users, such as your company, a group of banks, or government agencies. And there are hybrid public-private blockchains too. In some, those with private access can see all the data, while the public can see only selections. In others, everyone can see all the data, but only some people have access to add new data. A government, for example, could use a hybrid system to record the boundaries of Anne's property and the fact that she owns it while keeping her personal information private. Or it could allow everyone to view property records, but reserve to itself the exclusive right to update them. It is the combination of all these factors, decentralizing of the data, building trust in the data, and allowing us to interact directly with one another and the data, that gives blockchain technology the potential to underpin many of the ways we interact with one another. But, much like the rise of the internet, this technology will bring with it all kinds of complex policy questions around governance, international law, security, and economics. Here at the Center for International Governance Innovation, we seek to bring trusted research that will equip policymakers with the information they need to advance blockchain innovations, enabling economies to flourish in this new digital economy. Learn more about our work on blockchain technology by visiting our website and social media channels.
All right. So I like that video because I think it does a really good job of visually explaining the different types of blockchains, private, public, and hybrid. Now, before we go on, so I wanted to quickly take one step back and look at how did this become. So as you saw in the video, this is a peer-to-peer network. But this is the actual Bitcoin white paper. Anyone can go and view this. It's free online. I believe it's on bitcoin.org, but you can also just search, Bitcoin white paper and it'll come up. It's been unchanged. It's exactly how it was when it was published in 2008. But essentially, this is the narrative that introduced blockchain. And it was really for a peer-to-peer version of electronic cash that would allow online payments to be sent from one person directly to another. So again, eliminating that need for an intermediary. Now, this proposed a solution to a double spending problem. It allowed for timestamps and a hashing of on-chain work. One thing I wanted to point out was that in the video, we briefly talked about proof of work. We will get into this in more detail later, but this was the first type of consensus algorithm also introduced in the Bitcoin white paper. Now, what did this mean when it first happened? So when blockchain was first introduced with Bitcoin, all of a sudden we saw the emergence of cryptocurrency. And this kind of brought forth the very, very early stages of a new financial era that would take some, about 10 years before it picked up really like mainstream attention and started to prove that it had staying power. So I want to look at the differences between fiat currency and cryptocurrency because I think within these differences, we can actually see the value of blockchain. So with fiat, it's issued by a government, but in contrast to crypto doesn't need a central authority. It doesn't need a government to run and keep track of the currency and money supply. It's because of blockchain that it can record that information within the data itself. With fiat, we always see a delay between the transaction and settlement. Usually money changes hands, 10 to 20 times over just to settle and for whichever transaction we conducted to actually be final. Now with cryptocurrency, there's no clearing, there's no settlement. It removes a lot of those intermediaries, so it's more direct and concise. Now with fiat, there's a need for these intermediaries to also prevent fraud and loss. That is something valuable that they provide. They are able to detect if, there's a transaction with a well-known, crime organization. They're able to then use that information to prevent scams, to protect their citizens, et cetera. With crypto, since everything is verified by the network and baked into the blockchain, there really isn't a third-party service on top of that to prevent fraud and loss inherently. However, now we have a lot of things like centralized exchanges and other types of kind of cryptocurrency businesses that we interact with that provide this level of protection, but it's almost voluntary. So with fiat, it's baked into the system that you need certain government agencies to ensure that there is responsible handling of money. But with crypto, you do have the option to send money directly to and from each other. This also brings a little bit of risk because if you send money to the wrong address, it's going to be very difficult to reverse that and get it back. You would have to know the party with the wrong address that you had sent it to. So there are a couple of pros and cons on both sides, but the last one is probably the most important in my eyes. And I think with fiat, we have high transaction fees. We've seen the mishandling of money and irresponsibility of financial institutions as part of the 2008 financial crisis. But with crypto, we have this immutable transaction history. No one can go back and change data. It becomes very difficult to break, almost impossible to hack. So in this way, I think crypto provides a more secure, private, and sustainable way to interact with currency and money. Now, when we talk about a transaction, this is basically what happens under the hood of someone sending crypto from one person to another person. And it really shows how the blockchain works before we get into a video and start talking about it more in depth. So let's say we have Alice and she wants to send money to Bob. How that would happen on the blockchain is that the transaction would be represented online as a block. That block would then be broadcast to every party in the network, and it wouldn't have, Alice and Bob's information, but it would have the timestamp and the amount being sent from one party to the next. The actual account numbers and all of that would be hashed, so that would be kept hush-hush within this transaction. The network then approves the transaction is valid. They say, yes, Alice owns this, and she's going to send it to Bob at this address. Everything about this transaction is valid and good to go. Alice does have the funds in her account to send. Then they actually move the funds. So the block is then added to the chain, which then adds this kind of transparent, immutable other block in that long linear span of the history of this cryptocurrency. And then the money moves finally when that block is baked in. So with proof of work in Bitcoin specifically, this can take about 10 minutes because that's how long it takes for a block to get settled. Sometimes you'll see the transaction already move, but it'll on the front end, but on the back end, it'll still be moving through the blockchain. Now, while 10 minutes can kind of sound long, it's actually drastically faster than moving fiat currency from one party to another, especially if you're going over geographic lines and going from one geographic region to the next, where even more intermediaries slow the process down. All right, so how the blockchain works. This video, we're going to get into a little bit more technical. So the first one, we touched on the importance of blockchain, different types at a very high level. But now we're going to start talking about the technical complexities.
Hi, everyone. My name is Cy Venom, and I'm with the IBM Cloud team. Today, let's talk about blockchain. I'm excited to talk about this because I feel like there's a lot of misconceptions out there about the technology. And in addition, there's a lot of concepts that can be difficult to grasp. In this video, I want to dive into the fundamentals of blockchain. We'll start with the definition. Blockchain is a distributed and immutable ledger allowing you to track almost anything, tangible or intangible goods. Most of us are probably familiar with cryptocurrencies, where blockchain is used to track transactions. So to better understand how blockchains are distributed, let's start with an analogy. Let's say I'm with a group of friends and I lend my friend Pat $10. Now the friends see the transaction go down and they know that I have the correct amount of money. And in addition, they've essentially endorsed the transaction and they made a record of it. Now, next week, when Pat comes back to me to ask how much money I'd initially lent her, we could easily go to any one of my friends that have a record of that transaction. Now, blockchains are distributed as all of the nodes that are running in that blockchain network have a record of every transaction that's ever taken place. Now, that kind of lends itself to the distributed nature of blockchain. So although ledger technology has been around for some time, even simple ledgers, blockchain takes advantage of it by having a single source of truth and has a distributed nature where everyone has the same copy of that blockchain. Next, let's introduce the fact that blockchain is immutable. To do so, let's dive into the pieces that make up a blockchain. So in a block, we have three major pieces. First, we're going to have the transactions. So these are going to be all the transactions that occurred when that block was created. In addition, there's going to be a hash. A hash is essentially a digital fingerprint. So it represents the transactions that are in the block and is completely unique. So if any of the transactions were to be changed, the hash would also change. So let's pick a couple of letters for the hash. Generally, it's an alphanumeric sequence that's usually a lot longer, more secure. It's also going to have the hash of the previous block in the chain. So let's say we're right in the middle of a blockchain here, and we'll pick something for the previous hash, say maybe 2A. And so now let's move on to the next block. The next block is going to have its own set of transactions, as well as the previous hash, which corresponds to this one right here, as well as its own hash. And so on and so forth, we can kind of extrapolate all of the hashes and previous hashes. So you can imagine that if you were to want to tamper with any of the transactions that have occurred or change it, so for example, to change one of the transactions, this one, the hash would change. And because of that, the previous hash of the next block in the chain would now be incorrect. So to fix that, you would have to tamper with every single block in the chain, and that would immediately become apparent. So in this sense, blockchains are immutable and very tamper resistant. Now, the next thing I want to talk about is the idea of a permissioned versus a permissionless blockchain. So we'll start with a permissionless blockchain. Now, when most of us think of blockchains, we're probably thinking of cryptocurrencies, which are public and permissionless. Now, that means anyone can see all the transactions that have ever taken place. Now, identities are not exactly revealed. It's only the addresses that people have. But regardless, all the transactions are public. And in addition, anyone can register themselves to be one of the nodes in the network, essentially having a copy of the blockchain. And anytime it gets updated and new transactions are made, they would get a new block. So you have to imagine it's quite a problem for all of these nodes to have a copy of that blockchain. When new transactions come in, how do they reach a consensus on which transactions will make up the next block? That's done so using a consensus algorithm. Let's break down how this works for a permissionless public blockchain. So a client will first submit a transaction. That transaction will join a list of other transactions that have been made on the network. And then the next thing that'll happen, the node is going to start picking up those transactions, and it'll validate by looking through all of the transactions that have happened in the blockchain so far, that those are also valid. It'll kind of emulate a block and then start something called a proof of work algorithm. Now, this is a consensus algorithm that public permissionless blockchains use. And essentially, this is how they're able to reach a consensus on which block should be next. Essentially, it's going to be a very complex algorithm, cryptographic hash puzzle that all of the nodes are working together to solve. As soon as one of the nodes solves it, they've essentially unlocked the position of the next block. And what they'll do is they'll broadcast that position of that next block to all of the other nodes in the network, as well as adding it into their own blockchain. So a proof of work algorithm is actually quite consuming on the processing and the electricity on a global scale. So although it's kind of required for supporting public permissionless blockchains where anyone can be a node and anyone can submit transactions or submit their hardware to kind of enable the adding of new blocks, you don't want to take advantage of those kind of algorithms when you're working with blockchain for business. And this would be something like a permissioned blockchain. So in a permissioned blockchain, so this would be something like Hyperledger Fabric. You have the idea of pluggable consensus algorithms. Now, you don't want to do something like proof of work because solving those complex algorithms just to find the next block is not necessary when the nodes within a blockchain network are trusted. So that's one of the first concepts here. So pluggable consensus. Now, the nodes in a permissioned blockchain are trusted, so they generally know each other. In addition, they don't always just represent users, but entire organizations. So in this case, it's actually very important that privacy is one of the main kind of tenets of a permissioned blockchain. Let's take an example. let's say that there's a retailer that purchases 100 pounds of produce at $1,000. So we'll say it's a buy order for 100 pounds at $1,000. Now, the manufacturer receives the order from the retailer and says, okay, let's approve it. Let's make sure we have enough in the warehouse, and let's work with the shipping company. So they go to the shipping company and they say, okay, let's ship this 100 pounds, and it's going to cost them $100 to actually make that shipment. Now, there's some privacy concerns here. The manufacturer has to have all the information. That's fine. They need to know about the buy order that was placed as well as the shipment order that they've placed. But the retailer, although they need to know information about the buy order as well as the amount, as well as the kind of the price of it, they don't necessarily need to know how much it costs to ship it. But they might want to know when it was shipped and how much it was for. On the same hand, for the shipper, they need to know that they placed the shipment order, the amount and the cost of it. They need to know maybe when the order was placed, but they don't necessarily need to know how much the retailer spent. Now, the same goes for perhaps more retailers that the manufacturer might be working with. Now, if the manufacturer is offering a different price for the product for one retailer rather than the other one, it doesn't make sense for the retailers to know about the competing prices. So in this case, although all of the organizations are part of the blockchain, only the retailers that are part of the transactions that took place should be able to see that information. So in this case, in blockchain for business, it's actually pretty important that privacy is part of the blockchain, being able to control who can see particular transactional information. The last thing I want to touch on here is the fact that in permissioned blockchains, you can really make transactions more efficient. I think one of the most successful applications of blockchain technology is something called smart contracts. Essentially, this is code that's running on the blockchain, and whenever certain conditions are met, they're automatically executed. So in this particular example, whenever that retailer made that purchase order to the manufacturer for this amount of goods, there's probably a manufacturing agent that double checks that the order has all the necessary information in it. They then probably go with the shipping agency to make sure they can cover the shipment and that the warehouse has the correct amount of goods. They'll then make a shipment order. Now imagine if we could automate that whole process. That's what you can do with smart contracts. Essentially code that will make sure that all the necessary information is met, the warehouse has the correct amount of goods, and then it'll automatically create the shipment record. If any one of those conditions is not met, they could automatically release a refund to the buyer. This greatly speeds up the process of the contract for everyone involved, the retailer, the shipper, as well as the manufacturer. Thanks for joining me for this quick overview of blockchain technology. We've really only scratched the surface, so if you want to see more videos like this, be sure to subscribe. If you like the video.
All right. So I think he does a really good job on a couple of different notes. He really describes hashing. We talked a little bit more about proof of work. And then again, with that transportation example, you can see how blockchain can be applied to things besides crypto.
Hi, everyone. My name is Saida.
So moving on, I wanted to dive into encryption a little bit. So this is just an overview of what encryption is. I know I covered this in the very beginning, that example of putting a piece of sensitive data within a folder. But this is what it really looks like when we break it down. So let's say we have a sender and a recipient, and whatever's in this plain text document is confidential. So in more classic encryption, what happens is that it becomes encrypted. Then that ciphertext is what that document looks like when it's in transit to the recipient. And then a key is then used to decrypt that. Decrypt meaning that it changes it back from ciphertext to the plain text so that the recipient can see whatever that message was in its original form. Now, there are two different types of encryption. There is symmetric encryption and asymmetric. So symmetric is when you have the same key to both to close and then open that document. So if we look back at this first slide, symmetric encryption means that the encryption and decryption key would be exactly the same. Now, asymmetric encryption is a little bit more secure because you have one key that's encrypting it and then a different key to decrypt it. This provides a little bit more protection because they're unique keys for each type. Now, hashing, this is going to be our last video of this workshop, and then it's just my voice. But hashing is not exactly the same as encryption, but it's a fundamental part of blockchain, as we saw in this last video. But I wanted to break it down a little bit more. I think when it comes to blockchain, especially blockchain development, you're going to hear things like SHA-256, which is a specific type of hashing. And this is the most technical concept that we're going to cover today. Then we're going to touch on consensus algorithms, which are a little bit more broad and high level. And then we're going to bring it back into greater scope and talk about use cases. So hold on with me. And I promise this is just about a 5-minute video. And the most technical thing.
In simple terms, hashing means taking an input of any length and returning an output of fixed length. In the context of cryptocurrencies like Bitcoin, transactions are taken as an input and run through a hashing algorithm that returns an output of a fixed length. Let's see how the hashing process works. For this exercise, we're going to use the secure hashing algorithm 256, or SHA-256. In the case of SHA-256, no matter how big or small your input is, the output will always have a fixed 256 bits length. This is critical when dealing with a huge amount of data and transactions. Instead of remembering a large amount of input data, you can remember the hash to keep track. A cryptographic hash function is a special class of hash function that makes it ideal for cryptography. There are 6 properties that a cryptographic hash function needs to have in order to be considered secure. Let's go through them one by one. Property 1, deterministic. This means that no matter how many times you input the same data, you will always get the same result. This is critical because if you get different hashes every time, it's impossible to keep track of the input. Property 2, quick computation. The hash function should be able to return the hash of an input quickly. If the process isn't fast enough, then the system won't be efficient. Property 3, pre-image resistance. Pre-image resistance states that it is infeasible to determine the input data based on the output hash. Notice the use of the word infeasible instead of impossible. For example, suppose you're rolling a die. Instead of getting a specific number between 1 and 6 when you roll, you instead get a hash value that corresponds to a specific number between 1 and 6. How will you be able to determine what the original number was? All you have to do is find out the hashes of every number from 1 to 6 and compare it with your result. Since hash functions are deterministic, the hash of a particular input will always be the same. This means you can simply compare the hashes and find out the original input. This is a trivial exercise when dealing with 6 possible inputs, but when working with even slightly larger data sets, the difficulty of guessing a hash increases exponentially. The only way to find the input from an output hash is through brute force, that is, by making pure, random guesses. So what happens if you use this method? If you spend every second of every day guessing hashes without sleeping, you would be guessing hashes for the rest of your life, and you would never even come close. Neither would your children if they did the same, or their children, or their children. So while it is possible to break pre-image resistance by brute force method, it takes so long that it doesn't even matter. Property 4, a small change in the input changes the whole output. Even the smallest change in input must have huge ramifications on the output. This is a critical function that aids in making the function pre-image resistant. Property 5, collision resistant. Collision resistance means that each input will have its own unique hash. Having 2 different inputs that result in the same hash is known as a collision. No hash function is completely collision-free, but much like the timeline of the brute force attack we described before, it takes so long that it doesn't matter. Property 6, puzzle-friendly. This is a pretty complex property, and it's represented in some form by this complicated-looking equation here. But math is hard, so let's turn this into words and pictures. K represents a particular value chosen. In order to fit this property, the value has to be chosen from a significantly large distribution of points. To choose a number between 1 and 5, for example, would not be sufficient. Choosing a number between 1 and 1 septillion would be significant enough distribution for a cryptographic hash. This line here denotes concatenation. Concatenation means adding 2 strings together. If I were to concatenate blue and sky, then the result would be blue sky. So looking at the equation again, given a hash output of y and a randomly chosen point k, it must be infeasible to find an x value such that the combining of k and x will give hash output y. Woo, math. So what does all this stuff mean in blockchains? Why does any of it matter? The blockchain is a sequence of blocks that contain data, and a hash pointer that points to its previous block, hence the chain in blockchain. A hash pointer contains the hash of all the data inside the previous block. This small tweak is part of what makes blockchain so revolutionary. Imagine a hacker attacks block 3 and tries to change it. Because of the properties of hash functions, even a slight change in data changes the hash drastically. This means that any change made in block 3 will change the hash stored in block 2. This in turn will change the data and the hash of block 2, which results in changes in block 1, and so on. This is exactly how blockchains attain immutability. Any tiny changes in the data are immediately noticed and nullified by each preceding block. Essentially, the concept of hashing is a core part of what makes blockchains revolutionary and unique. Understanding how it works, as well as the security and efficiency it provides, is a key step towards understanding blockchain technology as a whole.
All right, so I know that was quite complex, but I think covering hashing is pretty vital to actually understanding, when we say that blockchains are super secure and allow so much privacy, hashing and encryption are really the fundamentals that enable that to happen. All right, so now we're gonna kind of just compare the two so that you have a better understanding of how they're used within the blockchain environment. So encryption preserves 100% of the original text. So if we're encrypting, say, an email between one person to the next, the full email is what would be encrypted. Where hashing produces a fixed length signature. So if it's a file or if it's just a couple of words, it's going to be about that 50 or 60 character length, no matter what. Encryption is reversible. So as we saw with both the asymmetric and symmetric versions of encryption, you basically undo the encryption in order to read the original message, where hashing is more of a one-way process. It's kind of like a one-way lock, and it's irreversible. Encryption produces a unique file, and hashing also produces a unique file. However, theoretically, you can possibly have collision where two things are hashed and they use the same hash, but there are two different forms of data that you're hashing. So this problem is being worked on. It's very theoretical in nature. This actually hasn't happened yet, as far as I know, but something that I wanted to just surface as we talk about these concepts. And then finally, and if you take one thing from everything we've covered on encryption and hashing, it's this. Encryption is perfect for transmitting and storing data, while hashing is better for strong critical data like passwords or account numbers. So if you take anything away from this slide, just remember the last line. Encryption is for transmitting and storing data in general. Hashing is much more specific for that kind of critical sensitive piece. Most organizations need both. So with most protocols that are blockchain based, they have both encryption and hashing at its core. Now I want to cover consensus. We have lightly touched on this in a couple of the videos when you've heard of proof of work. But these are some really big differentiators and why cryptocurrency has exploded. And now there are thousands and thousands of cryptocurrencies on the market. The actual definition of consensus is to find agreement. Now, when we talk about consensus in the context of blockchain, we're talking about a mechanism that allows users or machines to find agreement in a distributed setting. So this is something that is very specific to, the internet and digital world. How are you supposed to find agreement with a large group of people that maybe don't speak the same language and are distributed across different regions, different places who you've never seen? Consensus algorithms actually enable this, and we need that agreement in order for a decentralized technology like blockchain to operate. So there are two main types that I'm going to cover today. Proof of work is what we've covered. It's what we know best. It's what Bitcoin is based on. But another type of consensus mechanism that's emerged is proof of stake. I will cover the differences of both, but I want to walk you through how it actually works first. I will also not really touch on the other mechanisms, but there are a handful of others that are being tested and run in different projects. So the first here is proof of work. Now, this is where, miners mine. You have those computational puzzles to try and figure out the answer for about every 10 minutes. The algorithm adjusts the difficulty of those mathematical puzzles to make sure that it's about every 10 minutes. So if a ton of miners come on the network, it doesn't mean that it's going to speed up the time because the difficulty of the problem will just get higher. The same thing is if a lot of miners left the network and all of a sudden the block started to get a little bit more than 10 minutes, then the difficulty of that computational problem would then decrease so that we could still stay about 10 minutes. So you can see how there's this accordion effect that happens with proof of work. Now, the miners receive a block reward if they can solve that puzzle first. And this is what incentivizes them to participate in the network. Now, with a proof of work protocol, it's nearly impossible to attack. You would need what's called a 51% attack, meaning you have the power, computational power, of more than 51% of the network to add a malicious block or to maybe reverse the last block. Now, what does this mean exactly? It means that in order to hack Bitcoin, you would need to take over 51% of the nodes in the network. And with a distributed system like Bitcoin, like the Bitcoin protocol, it's pretty impossible to do. There have been a couple of theorists that have walked through like how you would actually try and do this. But if a hacker really wanted to do this, what they would gain from one block is not worth the astronomical cost it would take to actually do a 51% takeover. We're talking more money than any country has in order to do a one block attack. So it then becomes impossible because a hacker wouldn't go to that that length of effort for such a little reward. Then we will have proof of stake. So with proof of work, the benefits are that it's extremely secure. It definitely has showed that it has staying power. Since this became a thing in 2008, we've seen that, it hasn't been broken, it hasn't been hacked. We are able to upgrade it over time. So we are able to make improvements as we innovate and evolve ourselves as a society. And in that way, it kind of grows with us. Finding that consensus on those upgrades is also extremely hard. It's very difficult for everyone to agree that yes, this upgrade needs to happen. But every upgrade that has happened, because it has that overwhelming agreement, it has always improved the network for the better. These types of things are quality assured to an insane extent because so many people are in the network. Now, the drawback to proof of work is that it does take time and it does take energy. When you're talking about all of these mining machines working, the energy issue is very real. I think recently in the last week, Elon Musk actually threw a wrench into the whole Bitcoin game because he said that Tesla would stop selling their cars in Bitcoin because of the energy issue. Now, there are a lot of different theories as to why he did this announcement on Twitter. But basically the Bitcoin price went down about $10,000 within a week just because of this. And so the energy consumption problem is very real. I will note that over 50% of the energy consumed by Bitcoin is renewable energy. We definitely still have a ways to go in making it even more sustainable. And compared to the fiat system we run today, it pales in comparison. I think you can also, compare the energy consumption of Bitcoin to other things. Like, I believe there was a stat that said the Christmas lights in the United States take up more energy than the Bitcoin network. So then the issue arises of, well, what are we actually spending our energy on? However, this is a real argument, and energy is an issue. Climate change is an issue. Sustainability is important. So while we work to make our mining equipment much more energy efficient and distribute our energy more sustainably, proof of stake then became a thing. Now, proof of stake doesn't rely on miners. There are no miners to solve a puzzle and collect a reward in that specific way. Instead, you have a network of validators. And a lot of these validators use their own cryptocurrency holdings in order to power the network. So validators don't really receive a block reward per se, but they do collect transaction fees as a reward for staking whatever their claim is. Now, although this is faster and it consumes less energy, it's less decentralized in nature, because if someone in the network has an extremely large share of stake. So they have staked 20% of all of that cryptocurrency because they hold a majority of it. That means that they have an overwhelming amount of power within this protocol. It means that they have the power to make more changes, and that the likelihood of a 51% attack would actually be much more possible. While it would still be difficult, someone with over 51% stake in that specific cryptocurrency would have major influence. This is something I want to touch on because you may have heard of Dogecoin. And while it's very popular, it's a meme coin, there's really no utility to it. It was just kind of made for fun, but it really got picked up over time as people saw that they could make money off of it. But one key thing is that there are a handful of people that own the majority of Dogecoin. That means that if one of those people, or one of those whales, as they're termed in the industry, if they were to dump all of their Dogecoin, that means that because they had such a significant market share, that they would have then immense influence on the price of that cryptocurrency. So, for example, let's say my friend Alice owns 30% of Dogecoin, and she decides, well, it's time for me to get out. I want to buy a boat and I want to move to some island. She dumps all her Dogecoin. What happens to the price of Doge? It probably goes down because she had 30% of the whole network. And then everyone else that was holding Doge, there aren't any market signals. All of a sudden the price plummets. So while proof of stake is faster and a little bit more energy efficient, it's not necessarily as secure or as truly decentralized. Now, how is blockchain used today? So it's used in a myriad of use cases. I think before we dive in, I just want to quickly reiterate that blockchain manages and secures digital relationships as part of a system of record. So when we talk about the value here, this key piece that's bolded at the top, that can be applied to almost any system we interact with today because it provides distributed record keeping, it establishes digital identity, it's immutable, and it's decentralized. Most of these things will benefit any system we have today that's lying in a single server database, meaning that, let's say JP Morgan, they have all their information on one database, or at least on JP Morgan's databases. That provides a single point of failure, meaning that it's not decentralized. And if there was a hacker to get in, they'd be able to swoop all that data in one go. Now, use cases. This is just a very small sample size of how blockchain can be used. You have everything from land registry to supply chains, waste management, computation, real estate, music rights, creative rights, fine art, national security. There are so many different applications of how blockchain can be used. There are a ton of projects out there that are tackling, how to improve healthcare with blockchain, in terms of storing data, sensitive data on the blockchain, and also empowering people to take control of their healthcare data, which right now is siloed between healthcare companies. Things like music rights, where artists can actually retain the right to something instead of going through, 6 different companies that then take a large majority of the proceeds from that creative work. We've seen the explosion of NFTs this year. So by storing a certificate of authenticity on the blockchain of a piece of art, it, reduces the art forgeries that could happen. It actually, has a certification of, this is the original work by the artist. It also keeps a chain of the transactions of that piece of art. So right now, or let's say a couple of years ago, if someone made an oil painting and that artist sold that oil painting to someone for $10,000, that would be it in terms of what the artist gets from what they created. Then that painting might be sold from one owner to the next owner. It might be auctioned off later years for millions of dollars as it accrues value over time. But that artist, the original one that had made this work, only got that first sale of $10,000. So I think a lot of artists are seeing the potential of how NFTs can, make their art actually work for them over time, so that they have some sort of control and, I guess, more value from what they created, rather than it just going out into the ether. So again, blockchain can be applied to many different things. This is just the tip of the iceberg. There are a lot of projects out there tackling all sorts of issues. So I'd highly encourage some research. Now, group work. So we have about 10 minutes. So whether you're in a group of a couple people, a larger group, or by yourself, I think walking through these questions is really helpful for understanding blockchain, and letting all of this information actually sink in. So first, what is one system you could apply blockchain technology to that you interact with today? So think of something that you interact with in your day-to-day life, and think about how decentralization and blockchain could actually improve that. And then brainstorm the pros and cons. Why would it be better to be on a distributed ledger rather than a single server ledger? What benefits would this bring? Speed, security. Think through the different touch points that we worked on earlier today. Think about how encryption could benefit it, or hashing. Think about if there's any critical piece of data within the system. Usually blockchain can be an improvement in that way. And then second, you can do both of these or one of the other. I recommend doing both, especially the first question first. But the second one is, what is one social cause you care about that could benefit from blockchain record keeping? So go wild, use your imagination, think about something that you're passionate about and really care about, and then research if there are any active blockchain projects working on that. In most cases, I would say there usually are. There have been a lot of projects that have started in the last 10 years, a lot of nonprofits, a lot that are tackling things like carbon footprint, deforestation. I mean, your imagination can really go wild in terms of social causes, but think about it. And if you can't find any active projects, start your own. You have the complete power to, create your own blockchain-based system. Even if there is an active project that's similar out there, think about how you might be able to do it better, because you have the complete freedom to build it, develop it, and then get it out there in the world. Because this is all decentralized, you have a global stage that you're working on, and there are no permissions or blockades from other people joining that. So highly recommend you do the group work exercise. And again, thank you so much for being with me today. My name is Sam. Theblockhead.com is my website. You can reach me on there. You can also reach me on LinkedIn. Thank you.